Hello, welcome to Group 6's presentation on credit card fraud detection. My name is Karmen Keasler, and in our group we have Calvin Wang and Kevin Chiang. Today we are going to walk you through the importance of credit card fraud detection through our business use case, go over our primary goals for our project and our key findings. We will then go into a brief demo of how we trained our models and close out with our project learnings. So let's get started. Machine learning is crucial for credit card fraud detection due to its ability to analyze vast amounts of transactional data and identify patterns that indicate fraudulent activities. Fraudulent transactions often exhibit subtle patterns that can be difficult to detect with traditional methods, and machine learning algorithms, especially those using deep learning, can identify these complex patterns and correlations that may not be apparent immediately to humans. Fraudsters, as we like to call them, continuously change their methods to bypass detection. Machine learning models can be retrained regularly on new data, allowing them to adapt to new fraud techniques. I work for a fintech company who caters primarily to credit unions, and I had the opportunity to meet with our risk intelligence team to further understand how our enterprise leverages machine learning scoring rules and neural network scoring to fraud monitor our for our credit unions. And the solution our company provides pulls in both Visa and MasterCard's fraud risk scores in real time and places them into our neural network with rules that we've created. And they take it even further. So, in addition to these scores, and in conjunction with things such as the FICO scores, payment network scores, and machine learned scores, they add in personalized data. So, for example, if I had $300 taken out of my checking account for an online retailer, and I get a ping from my bank asking if this was me or if it wasn't, and obviously, if I pick that I wasn't, they're going to make me whole. They will make sure that the $300 gets put back into my account. But to be honest, I can't help but feel like I've been robbed a little bit, even though they've made me whole and they did their due diligence as a financial institution to really, put that back into my account. And so, what our solution actually helps with is it'll help add in some of my personalized data as a member and look at the trends of like my shopping habits, locations, and the merchants that I shop with. And when there's an anomaly detected, they will notify you as a member or to your credit union, in my case, and they'll let them know, hey, this is an anomaly, and it's likely that fraud will occur versus being reactive. And so that makes me a little bit more appreciative of some of these predictive analytics that we're able to provide through machine learning. Our primary goal of our project was to predict whether fraud is occurring. And to do so, we use various classifiers such as random forest and logistic regression, and metrics such as accuracy, precision, recall to help evaluate the model performance, focusing on the trade off between catching fraud and minimizing false positives. And although the data set that we used is synthetic and really transactional, we were able to identify some patterns and anomalies that did occur.
In our data set, we find that the number of transactions that are labeled as not fraud greatly outnumber the number of transactions that are labeled as fraud. While this is representative of a real world environment, imbalanced data sets can pose a challenge for predictive modeling, where the model can bias towards the majority class, which in this case is the transactions labeled as not fraud. To address this issue, our group has opted to undersample the majority class in order to balance the training dataset. With over 1 million entries in the training dataset, undersampling is the more appropriate choice in an effort to reduce training time given our limited computing power and time. We leave the test dataset as is to reflect the real world environment. We instead prioritize recall, F2 score, and the area under the precision recall curve for the reasons listed above. A high recall ensures that most fraud cases are identified as such, minimizing the number of false negatives. The F2 score, like the F1, considers both precision and recall. However, the F2 score puts more emphasis on recall over precision. The area under the precision recall curve reveals the trade-off between precision and recall. It is more informative than the area under the ROC curve for highly imbalanced datasets because it focuses on the minority class. Classification accuracy is a measure that reflects how well a classification model performs by calculating the ratio of correct predictions to the total number of predictions. In imbalanced classification problems, achieving a high accuracy can be misleading. Using our dataset as an example, with a 100-to-1 class imbalance in the training set, simply predicting the majority class every time would result in 99% accuracy. For fraud detection, which typically involves highly unbalanced datasets with high amounts of legitimate transactions and few fraudulent ones, it's important that we evaluate the model using metrics that can effectively handle class imbalance and effectively prioritize false negatives. The reason false negatives are more important than false positives is because of the cost associated with letting a fraudulent transaction slip through rather than mistakenly flagging or blocking a legitimate transaction. And now we are going to go over our Jupyter notebook. We start by importing all the modules needed for this project. As the dataset is already split by the uploader, we import the training and testing data separately. We take a look at the imported dataset to get a better understanding of each column and consider the pre-processing needed to handle this data. The data types of each column are checked to see if there is anything out of the ordinary in case a column's data type needs to be converted. Identifying the data types will also help with identifying numeric and categorical columns when pre-processing our data. IsNull is used to check for missing values, which we can fill or drop the row entirely. In case of duplicate entries, we use drop duplicates to remove these rows. We then begin visualizing our dataset, starting with understanding the amount of data we are working with and the target class distribution. With over 1 million simulated transactions in this dataset, our group decided to undersample the majority class in the training set to reduce training time given our limited resources. The testing dataset is not quite as large as the training dataset, and the target distribution is similar. We use sample to reduce the majority class and balance the target to a 50-50 distribution in the training dataset. We created a bar graph to visualize the correlation between fraud and our features and noted that the primary feature that impacts our fraud prediction model is amount. However, depending on which business use case we can choose, such as fraud by age, fraud by location, other features would likely be correlated. Given that this is a synthetic dataset, the number of features are very limited compared to datasets used in the real world. In a previous slide, isNull.sum showed that none of the columns contain any missing values, so drop NA is not required for this dataset. We then split the target from the rest of the data. Because the dataset was already split into training and testing, train test split was not used for this process. The data types of each column are used to categorize the columns for pre-processing. An exception here is zip code, which is a numeric data type, but contains categorical information. Thus, we drop zip code from the numerical columns and append it to the categorical columns. We then apply a scalar to the numerical columns of the data and one hot encoder on the categorical columns. Finally, we check the number of features in both the training and testing data to ensure that they match.
The first machine learning model that we used was the ridge classifier. Ridge classification is a technique used to analyze linear discriminant models. Ridge regression is the preferred form of regression when the goal is to minimize the impact of less important features while keeping all the variables inside the model. As you can see, we used a function called ridge classifier, and we had to predict on the test set. After having a predict on test set, we had to output the accuracy, precision, recall, F1 score, and F2 scores. We also evaluated our model using a precision recall AUC. The precision recall AUC, or PR-AUC, is an evaluation metric that's used for binary and multi-label classification problems and algorithms. You can see our results on the right, where the metrics are printed up top. There's a confusion matrix in the middle of the image on the right, and there's also a classification report at the bottom of the image on the right. For this exact model, we had an accuracy score of about 99%, a precision score of about 0.6%, a recall score of 0.4%, an F1 score of 0.0051, an F2 score of 0.004, and AUC-PR of 0.007. To interpret these values, we could say that our model is pretty accurate, but it's also very imprecise based on precision score and also the recall score. This shows that our model overpredicts instances of fraud, which gave it low F1 and F2 values. And our AUC-PR score determined that it's not able to balance precision and recall effectively, so it's not a very strong model. In order to improve on our poor findings in our last model, we can use a function called grid search CV, also known as grid search cross-validation. This is a technique that is used in machine learning to help search and find the optimal accommodation of hyperparameters for a given model, and it's in the sklearn package. After running the grid search CV, we found that the best parameters were alpha, solver, and LSQR. We then fit the model again and had to predict on a test set. After running the model again, we had to output our findings on the right-hand side, similarly to last time. So we had our metrics printed out at the top of the right side, we had a confusion matrix printed out below it, a classification report, which you can see as a matrix below the confusion matrix, and also we added a visualizer this time, so you can see a bar graph at the bottom, which compares all of our scores together. So to summarize our findings, our ridge regression classifier, when it's trained on the best parameters in our dataset, had an accuracy score of 96.01%, a precision score of 6.42%, a recall score of 68.76%, an F1 score of 11.75%, F2 score of 23.38%, and an AUC-PR score of 37.65%. These values indicate that this model is very accurate as seen from our accuracy score, but is also very imprecise given the precision score, which is 6.42%. These scores indicate that the model overpredicts the instances of fraud, which also gave it a lower F1 score. The recall for positive cases is somewhat high, as seen from the recall score, which is 68.76%, which therefore gave an F2 score that is much higher than the F1 score, as seen as the F2 score of 23.38% versus the F1 score of 11.75%. The AUC-PR, also known as the area under the precision recall curve, indicated that our logistic regression classifier isn't good at balancing precision and recall effectively, and is therefore not a very strong model, but is still pretty acceptable among machine learning standards. The second machine learning model that we used was logistic regression. Logistic regression is a method and a supervised machine learning algorithm that's used to build models between two variables that describe the relationship between a dependent variable and one or more independent variables. It's often used for predictive modeling, such as fraud detection, which is the case that we had, disease prediction, and churn prediction. We ran the model and had our outputs shown on the right-hand side. As you can see, there are the evaluation metrics up top on the image on the right-hand side. There's a confusion matrix below it, and there's also a classification report matrix at the bottom of it. Our logistic regression model had an accuracy of 98%, a precision score of 11.1%, a recall score of 41.67%, an F1 score of 17.6%, F2 score of 26.97%, and an AUC PR of 26.5%. Similarly to the previous model, we improved on our model by running grid search CV in order to find the best parameters in order to rerun a model using the best parameters. We found that for logistic regression, the best parameters were the variables C, solver, and saga, and we reran our model using those parameters as well. After rerunning logistic regression using the variables that we found from grid search CV, which are best fitting variables, we found that we had an accuracy score of 95.66%, a precision score of 6.2%, a recall score of 72.59%, an F1 score of 11.43%, an F2 score of 23.11%, and an AUC PR value of 39.45%. This indicates that this model is very accurate as seen from the accuracy score, but also very imprecise as seen from the precision score, as it overpredicts the instances of fraud, which also gave it a lower F1 score. The recall for positive cases is moderately high, as seen from the recall score, which gave an F2 score that is higher than the F1 score. The AUC PR indicates that our logistic regression classifier is a poor but somewhat acceptable model, given that it's not great at distinguishing between fraud and not fraud when considering both precision and recall. The next machine learning model that we used was random forest. The random forest classifier is a commonly used machine learning algorithm that combines the output of multiple decision trees to reach a single result. We set up and ran the random forest classifier algorithm, and our outputs are shown on the right-hand side, where we have our evaluation metrics up top, our confusion matrix in the middle, and a classification report or matrix at the bottom of the image shown on the right-hand side, similar to last time around. We had an accuracy score of 96.6%, a precision score of 7.5%, a recall score of 68.8%, an F1 score of 0.13, an F2 score of 0.26, and an AUC PR of 0.382, which are better metrics than the previous algorithm that we showed. However, like any machine learning algorithm, it can be further improved, and we did so by running grid search CV on it again. We found that the best parameters for our model were the variables max depth, max features, min samples leaf, min sample split, and n estimators. Similarly to previous algorithms, we found that adjusting our model using grid search CV and using the best variables or estimators found from that model improved our model yet even further. To summarize our findings, which are shown on the right, we found that our random forest classifier, when trained on the best parameters in our dataset, had an accuracy score of 95.99%, a precision score of 8.6%, a recall score of 97.58%, an F1 score of 15.81%, F2 score of 31.79%, and an AUC PR of 53.09%. This indicates that this model is very accurate as seen from the accuracy score, but is imprecise as seen from precision score, which is 8.6%, as it overpredicts instances of fraud, which gave it a lower F1 score. The recall for positive cases is very high, however, as seen from the recall score of 97.58%, which also gave it a higher F2 score as well, at 31.79%. The AUC PR indicates that it's a moderately good performing model when considering both the precision and the recall scores, which are all over 95%. So in conclusion, out of the three algorithms that we use, which are ridge regression, logistic regression, and the random forest classifier, we found that when weighing the key metrics of accuracy, precision, recall, and AUCPR, the random forest classifier is the strongest at predicting credit card fraud, as it balances both precision and recall while maintaining the highest scores in all the accuracy metrics. To give our project a very brief summary, we can say that machine learning is crucial for credit card fraud detection due to its ability to analyze vast amounts of transactional data and identify patterns that indicate fraudulent activities. Thank you all for tuning into our project, and I hope you guys learned something. I'm sure Karmen and Calvin can attest that we all learned a lot during this class, and hopefully you guys did too. Thank you guys, and see you all around to next time. Bye bye.